So this is the second to last video for Chapter 7, Electricity Magnetism. Today we're going to take a look at some things called transformers. And, at the beginning of each class, I like to talk about what we've done so far in the chapter. So a quick review. Part A was just permanent magnets. Part B, two different ways that you can make magnetic field, either the long straight wire or the coil of wires. Turns out we're going to be coming back to that coil issue today. Two ways that you can find a force from a magnetic field. It could be on a single charge or a whole bunch of charges going down a wire, otherwise known as a current. And we have two ways of finding voltage when you've got changing flux. It could either be that one that talks about coils, that change in flux over time multiplied by the number of coils, or if it's just a wire cutting across a magnetic field, we could go with the BLV. And we did talk about how motors have that counter torque and back EMF. Now let's take a look at transformers. So transformers, first thing that comes to mind when you think of transformers might be like, oh, like robots in disguise. Like, wow, okay, that's kind of cool. But no, not the transformers we're talking about. We're going to be talking about these transformers. They can be very, very small, like this yellow one here on this circuit board, or very large, like the ones that you'll see hanging on telephone poles for power distribution. And their job is to actually change voltage levels. They can make voltages larger or smaller. But it turns out they only work with a very special kind of electricity where the currents are continually oscillating, going back and forth, and we call those alternating currents, right? So we just abbreviate that as AC circuitry. Now, everything you've been doing up until today has been steady current, what we call direct current or DC. But now we're going to be talking about some AC, some alternating voltages, like a sine wave. And that's the only kind of voltages that these transformers can work on, whether they be small or whether they be large. All right, the parts of a transformer. Well, on your page there, you've got kind of a little simplified schematic. I've also got some pictures here just so you can take a look. These are just on some circuit boards. The key thing with transformers is that there are two coils. So you can see on this circuit here, there's a coil of wire here, almost going about halfway around a little torus, a little half circle there. And then we've got another coil over on this side. So these transformers have a couple of coils to them. One of them will be where we put our input voltage, and the other will be where we have the output voltage. And they're usually called the primary and the secondary. But if you want to call them the input and the output, that's totally fine. Here's another pair of transformers as well, and there's one coil here. It looks like it's with some thicker wire, and then there's another coil there, a little harder to see, much thinner wire, probably has a lot more wraps of wire to it. So the parts, you've definitely got these two coils, right? The input coil and the output coil. Basic operation, what happens with a transformer? Well, you begin by putting in an alternating voltage into that primary coil, into that input coil. Okay, so imagine maybe on these transformers that this coil on this side is the primary, and so some alternating voltage goes in, and that creates a changing flux inside that coil. And there's an iron core that links those two coils together, so any changing magnetic field in this one is magnetically linked to the one right beside it. So we have an alternating voltage on the way in, creating an alternating magnetic field in the iron core, which is directly connected to that secondary coil. So that changing magnetic field, that changing flux of magnetic field in the core now generates a voltage at the secondary coil. So by putting an alternating voltage on the inside, we're going to get an alternating voltage show up on the output side. Transformers only work with Faraday's law of induction, which means you have to have changing magnetic field. So if you put an AC voltage in, then it works great because that will create a changing magnetic field in that iron core linking the two coils. But if you put in direct current with a battery, right? So if you had a big battery over here, it would create a steady magnetic field, and the steady magnetic field in the secondary coil would do nothing. It wouldn't generate any voltage at all. So these devices only work with alternating voltages, or what we call AC circuitry. Okay, the variables that we're going to be playing with. We're going to have 6 of them. They come in pairs. For each side of the transformer, we're going to be talking about the number of wraps of wire. Okay, so capital N is just the number of wraps of wire you have. And if we put a P on there, then it's the number of wraps on the primary side. And an S would be the number of wraps on the secondary side, the output side. V's are going to stand for the voltage on the way in or the way out. P for in for primary, S for the way out for the secondary, and I will be how much current is flowing in each of these coils. But remember, the coils are separate, so they can have different voltages on them, they can have different currents through them, and obviously they can have a different number of wraps of wire, a different number of N values to them. The equation, well, we're going to make this equation a little bigger in a moment, but we're going to start off with just this. Now, the little red arrows, I've added the little red arrows in there just sort of for emphasis. I'm going to take them out just for a second. In fact, those are some pretty bad looking red arrows. I just wanted to, with the red arrows, highlight how easy this equation is to remember. What it says is that the voltage is proportional to the number of wraps of wire. So by me putting these red arrows on there, really, and they were not very good looking red arrows, I was just trying to highlight how easy it is to actually remember this. So by looking at this and seeing that, hey, yeah, it's secondary on top and primary on the bottom, it's actually pretty easy to remember. Now, it's on your formula sheet, but it's almost like you don't even need the formula sheet because you've got the exact same thing, top and bottom. So there's the kind of equation. We'll modify it a little bit in a minute and add the currents in there, but for now we're going to start off with this. And so what I'd like to just highlight is that the voltage is proportional to the number of turns. If there are more turns on one side of the transformer, then that side of the transformer is going to have more voltage on it. Okay, that's what we mean by saying the voltage is proportional to the number of turns. And by turns, I just mean wraps of wire. So sometimes we'll say coils, turns, wraps, whatever you want to call it. So here's a little zoomed in picture of those transformers, and what you can see is over on the left side of these transformers, we've got some fairly thick wire, right? And there are, a fairly large number of coils there. But on the other side of that transformer, we've got some really thin wire. So thin, it's like hard to see. So it looks like on this side of the transformer, there are many, many, many more wraps of wire. That tells me that on the left side of this transformer, on this side over here where there are a small number of wraps of wire, there's going to be a small voltage. But on this side of the transformer where there are more wraps of wire, there's going to be a bigger voltage. Now, which way is in and which way is out? Which one's primary, which one's secondary? That's up to you. You can wire this either way. But the side that has more wraps of wire, usually thinner wire, is actually going to have more voltage to it. So more turns means more voltage, right? Nice and easy to remember. Transformers that are wired in a way to increase voltage are called step-up transformers. So I'm just going to go back to my picture. If your general flow for your electricity here was kind of in this direction, so you're inputting on that coil that has very few wraps and outputting on the many, many wraps, that will step up your voltage. That's a step-up transformer, and you can reverse it. You can say, well, what if I want to lower the voltage to make it safer, to make it lower? Absolutely. That's going to be what we call a step-down transformer. So transformers that decrease voltage, those are called step-down transformers. Now, it's important to know that a transformer can be wired either way. So you don't have to ask when you're buying transformers like, oh, well, is this a step up or step down? It's how you wire it, right? The transformer is going to have more wraps on one side than the other, usually. That way you can wire it up either way. Okay, let's try out a simple little example here. We'll see how this goes. Now, just double checking. I don't know if you guys have this in your notes. Probably should have. You're going to need to find a little spot to put this question in. It will actually be pretty short though. If you've got a transformer that has 80 coils of wire on the in and 2,400 on the secondary, if there's 120 volts going in, the question is how much comes out, right, on the output side. Again, I'm not too sure you have a spot for this, but it won't take a lot of room. You might be able to sneak it in just at the bottom of your page there if it's not in your note package. There's the equation. Super simple, right? Throw in the values that we know. We know every single thing except the secondary, the output voltage. And when you just do some cross multiplying to find out the answer, it ends up being really, really large, 3,600 volts. Now, I spent a second there to just reduce that 2,400 on top of the 80 to get that 30 to 1. Sometimes people like to talk about that ratio. They'll say, oh, this transformer has a turns ratio or a voltage ratio of 30 to 1, meaning one side has 30 times as many wraps as the other. So you could step the voltage up by a factor of 30, like we did, or down by a factor of 30. Okay, you could wire that one either way. So it's kind of neat. We actually made this voltage rise up to 3,600 volts. And you might be thinking, oh, well, maybe I can actually power Penticton this way with a 9-volt battery. Well, no, you can't. And we're going to see that issue coming up right away. Here's the catch. And I think you do have these notes in your package. The catch is this, and I should tell you, the math behind this, the behind-the-scenes math is very complicated, but the final result is actually pretty simple. You can't get more energy out than you put in. Or speaking in terms of how fast the energy is going, you can't get more power out than you put in. So power, the wattage, is conserved. It's constant. In and out will be the same number of wattage, the same number of watts. So sure, you might be able to kick the voltage up to 3,600, but you as an electrical engineer must create a story where the I goes down. And if you try to cheat, then there's this feedback mechanism mathematically that will try to stop you from cheating. But it will allow you to raise that voltage up to 3,600, but the circuit must have a lower current on that output side. So I'm just writing down I and V multiplied together because that's what power is. So I'm just saying with this equation here that the power on the primary is got to be the same as the power on the secondary. There can't be more power coming out. Now if I rearrange this equation so that Vs sits on top of Vp, kind of mimicking the transformer equation we've got so far, I can get to here. So all I've done is I've taken the idea of power being conserved, that equation that says V times I equals V times I, and I've rearranged it to create the blue and the green fractions here. The blue and the black fractions we've already talked about. Now the red arrows, that's just me kind of highlighting this story. Wow, the blue and the black are easy, right? Secondary's on top, secondary's on top, primary's on the bottom, primary's on the bottom, but the currents are flipped. Okay, they're actually kind of flip-flopped around. They don't follow the same pattern, and that's just to make sure that the power is actually conserved, that it's constant. So this is an example. You'll find it on your next page. It's actually at the bottom little corner in a box. This is as complicated as I can make the story. I tried to get totally convoluted here and just mix everything up, and I can't make the story more confusing than this for transformers. So if we can get this dialed in, then we're good to go. Now, the page you've got is this a little page I've created, that transformer organization page. It's just a page where you can kind of see everything at once. Okay, and you don't need this page for every single question. It would be overkill. But if you want to, you can kind of look back at this as a guide and see, well, how does this story work? So at the top of the page, I've just got my 6 variables, the 3 for each side of the transformer. Right here is the kind of the guts of it, the transformer equation and how the current is flip-flopped. Power is conserved, so in and out, those 2 powers are the same, those 2 wattages. And don't forget, you can still do Ohm's law over on the output side. And so it's a story about a little toy train, and for safety's sake, we only want to have 5 volts on the train because it goes into the track, and little kids might lick the track or something like that, so we've got to be careful. The train will have a resistance of 2 ohms, and we're going to use a transformer to take the 120 volts from the wall. We're going to step it down to that nice 5 volts for safety. Okay, and you can see that we know that there are 7,680 wraps of wire on the primary. And there's some things to figure out. We're actually going to figure everything out we can in this story. Okay, so let's take a look at where we can fill some numbers in. So at the beginning, just in red, I'm going to go and fill in all the numbers that were just given to me. They told me that the input side, the primary side, would be 120 volts. Great, put that in there. Secondary, the output, for safety, we're going to get it down to 5. Primary wraps of wire, we know 7,680. I don't know the number of turns on the secondary. I don't know any of the currents at the beginning of the day. I'm going to fill those numbers in everywhere I can, okay, just so you can kind of see the big picture here. Okay, so the transformer equation, oh, hey, look, we've got a complete fraction there. That could be helpful. Could do some cross multiplying to get to the ends. Stuck on the eyes though, right? No way to figure the eyes out from there. Looking at the power story, the wattage in equals the wattage out. Well, that doesn't reveal too much right now. Right? I've just got some voltages, no currents, no powers. Ooh, that's interesting. Ohm's law on the secondary side. I do know that I want 5 volts on the way out and 2 ohms of resistance there, so that's good. Let's see where we can go now. We'll start filling some boxes in. And again, this page is a bit overkill, but I just wanted to show you big picture, all the stuff we can work with. First thing, I can tell you this is a step-down transformer because I'm seeing the voltage go downhill. So if the voltage goes down, then we'll call it a step down. Now, if the voltage goes down, the current will go up. But voltages are how we decide that this is called a step-down transformer. Okay, next place. Let's see if we can start working with some cross-multiplying here with the transformer equation. 5 times 7680 has to equal 120 times the number of turns on the secondary. Super easy equation to solve there. And we see that there are 320 wraps of wire on the secondary. So I'm using that big transformer equation to kind of get rolling here. So I can put in my 320 number of turns on my secondary. All right. Just looking at the number of wraps of wire there, people might ask you, oh, what's the turns ratio, right? Oh, well, we got 7680 on the input and 320 on the output. So there's your ratio. You might want to reduce it down to like lowest terms, and you can say, yeah, 24:1. Now, most of the time people don't really care whether you say 24:1 or 1:24 unless they specifically say, hey, what's the ratio primary to secondary? Then you'd have to say 24:1. Or if they were to say, what's the ratio of secondary to primary? Then you would have to say 1:24. But if they just say, hey, what's the ratio? Call it whatever you want. 1:24, 24:1, it's all good. Okay, let's go down to Ohm's law here. We can do that Ohm's law on the output side, and it looks like there is 2.5 amps flowing on the secondary. So I can fill that in anywhere I see it here now, like right here. 2.5 amps. I could even fill it in here, right in my power relationship. Okay, so let's see where we can go with this 2.5 amps that we've got. Just by doing some cross multiplying, I can figure out that the current in the primary on the input side is pretty small, right? So where it had a big voltage of 120, we've got this small current of only 0.104 amps, or you might say 104 milliamps. Didn't even really need to worry about the power, but you could figure it out here now if you want. Sometimes people might give you wattages, right? So I've got my current in the secondary, 2.5 amps. That's 12.5 watts. And I'd have 12.5 watts on the way in too if it's 100% efficient. And 0.104 works perfectly. So there you go. That page, again, a little bit overkill. The main relationship is actually happening right here. Right? This is the main equation of the day for transformers. But do be ready to do Ohm's law or a power calculation if you need to find something that's missing. Sometimes that can happen. So that finishes up our second to last lesson for the chapter. And then the last lesson is actually pretty short.